So, quick review. We did the candle trick and decided that diffusion is what happens when stuff is dissolved in a solution and it's concentrated highly somewhere and then appears to move outward. What it's really doing is just random motion, but the net effect is that the stuff goes from high concentration to low concentration until there is no difference anymore. And we call that equilibrium. Now that's the easy stuff. That's where some things can actually get through a cell membrane. A lot of what you'll do to prove to me that you know how this stuff works, this transport works, is what I call beaker problems. So let's look at some simple beaker problems that just involve diffusion. A beaker problem is just, I'll draw a beaker for you with water in it, and you'll just have to trust me that that is a semi-permeable lipid bilayer cell membrane, okay? And I will show you molecules in that solution, and I'll always tell you what they are. And you'll know that oxygen and carbon dioxide are the molecules we'll use that can diffuse across the cell membrane. So the question is always going to be, given that these oxygen molecules are concentrated where they are, in the very next moment, what goes where? Does that make sense? Why I see a lot of furrowed eyebrows. Okay. So then what goes where? Ethan, what goes where?
They go to the center.
They being
The cell membrane.
We have a bunch of oxygen highly concentrated outside the cell.
Oh, the oxygen molecules.
We'll go
to the center.
To the center. We'll go into the cell. Yeah? That's the answer that I would expect. Typically, I expect arrows and a sentence as an answer for a beaker problem. So the arrows and a sentence on this one would be that. Right? Arrows in, oxygen goes in. You gotta tell me what is going where, because what if you meant water, right? And we will soon. How about the second beaker? Dominic, second beaker.
Oxygen would diffuse out of the cell?
Correct. The answer to this one would be oxygen diffuses out. These are the easy ones. Okay? But you got to know which things can go in and out and which ones can't. And I'll just tell you, the example is always going to be carbon dioxide and oxygen. I'll use different symbols for both. Those are always going to be able to get across the cell membrane. Also water, but that comes in our next concept. So when you see a beaker problem where it's something that can cross, it does. It goes from high to low concentration. Any questions there? Cool, because now we have to deal with something a little more complicated. We have to deal with what happens when stuff can't cross, when stuff is stuck on one side or the other. And the sort of counterintuitive thing that happens when stuff is stuck and can't cross a membrane is that the thing that can always cross does. The thing that you don't think about because you're mostly made of it does cross. And it crosses in kind of a backward way than you would expect. And that process is called osmosis. Osmosis, the definition is diffusion of water across a membrane. And the thing about that is you kind of have to do a little bit of mental gymnastics in order to predict which way the water is going to move. Because you have to stop thinking about solute concentration and start thinking about water concentration. I'll say that again. You have to stop thinking about solute concentration and start thinking about water concentration. The basic idea is this. When molecules are stuck like that, there's a bunch of, say, sugar molecules stuck inside the cell. Salt molecules stuck outside the cell. And sugar and salt are the solutes that I use in the beaker problems, just so you know. What happens is water starts to move, and it moves from high to low water concentration, following its own rules of diffusion, But what that means is that it's actually moving from low to high solute concentration. This is going to take a bit to really understand. And even when you understand it well enough to predict things, you still don't really totally understand it. You kind of just have to accept that it works. A beaker problem or two. Everybody caught up? Any more time? So now it's not oxygen anymore. Now it's sugar. Big round circles mean sugar. And we have similar situations, except that those things can't go from high to low concentration like they would if they could cross. They're stuck. And so now the same question. What goes where? Keep in mind what we said, which is that what's going to happen is water is going to move instead, and it's going to go from high to low water concentration, which is the same as low to high solute concentration. Sam, which way is the water going to move in that first beaker?
Inward.
The water is going to go inward. Why?
Or the water.
Yes, because these can't go inward because they're too big to cross the membrane. So now you got to do this little mental flip and think about water concentration. Start with this. Where is the water most highly concentrated in that beaker? Where is there the most water? In the middle, right? Because there's less junk floating in it. So if we're going from high to low water concentration, which way is that? That's out. Yeah, what's going to happen is this cell is basically going to lose water. Water is going to leave. Did you draw the diffusion ones? Nobody asked. You should have. Draw these at least. We can go back to the diffusion ones. By the way, we have a name for this kind of solution. The kind of solution that makes water leave a cell is called a hypertonic solution. This is major. It means something pretty important to living cells. That if you concentrate a bunch of molecules in solution outside them and they're stuck, that cell's going to lose water. You know, think dehydration. Think, salty stuff makes you thirsty. Next, second beaker. Logan, what goes where? It's hard not to think about that sugar leaving, but it can't. So what goes where?
Would the water go out of the cell?
Out of the cell? Why? Remember we said the water goes from high to low water concentration, which is the same as from low to high solute concentration. Where is the water highly concentrated? Outside. So what is high to low water concentration? What direction is that?
The water would go in the cell.
And that's what happens. Now keep in mind, you could have also said, okay, low to high solute concentration. There's low solute concentration here, high here. It means that way. It's the same answer. The first way to think, and you can get these right in one of two ways, and it's just up to you. I think the more correct way is to think in terms of water concentration, high to low water concentration. But if it's easier, you can think of the water basically compensating for the solute. The water, we really want the equilibrium to be there, so the water's going to try and go in.
Will you come to the attendance office, please?
The water's going to try and go in to kind of try to dilute. Not that water has intentions, but if it's easier to think of that way, the water tries to go in to dilute the solute that's packed in there. Okay, so water enters the cell in this case. And the name we have for the kind of solution that makes water go into a cell is hypotonic. Yes?
So the water's going to kind of go wherever the solute is?
The water is going to go to wherever the higher concentration of solute is. Yes, because it won't always be that there's no solute outside and some inside. It might be that there's some outside but more inside. Water's still going to go in. Good question. Yeah.
Sorry if I missed it. What happens to the particles in the middle of the cell?
What happens to them? They stay there. And what happens to the cell if more water goes into it? And it swells up a little. And can that force be strong enough to pop a cell? Yes, it can. Yeah, absolutely. It can be enough to lyse a cell. If we were allowed to work with blood, I used to have students draw their own blood for a couple of different labs with a sterile lancet. And then if you put that blood in distilled water, which is water with no solutes in it at all, the cells would pop. Powerful stuff, osmosis. By the way, the third type of solution where they're equal is called isotonic. That's worth writing down. I'm about to give you a page of beaker problems that you will be working. The answer is always going to be arrows and a sentence saying what goes where. This time I won't make you name solution types. That'll be on the second set of beaker problems. But the other thing we are going to do, because this is so very counterintuitive, this osmosis stuff, these beaker problems, you really don't believe it yet. And so what we need to do is set up a real life experiment where you can prove that this works. And the way we're going to do that, and I encourage remote learners to do the same thing, because all you need is a plastic cup. It doesn't even have to be plastic, something to contain one store-bought egg. And today for our setup, and this is just setup, we don't have to do anything else. All you're going to do is you're going to put your one egg in your plastic cup, and then you are going to cover that egg. And I would fill the plastic cup kind of up to like about an inch and a half below the surface. And then you're going to use white vinegar, white household vinegar, to cover that egg in that vinegar. And we're going to leave those until tomorrow. Does anybody know what's going to happen? Well, the weak acid in vinegar is basically going to knock the calcium ions off of that egg and decalcify it. And we're going to remove that shell. It'll basically turn into foam mostly. Yeah, and what we'll be left with, you know what is under the shell, right? Membrane. Not quite exactly the same as a cell membrane, but it does let water pass, so it does undergo osmosis. And so we are going to prove that osmosis works using a weird kind of gross water balloony egg. The setup is simply to cover that egg in vinegar today, and I'll give you instructions for that in a second. And then you have your beaker problems to work on for the rest of the period. Let me turn this off.
Sorry for the interruption. Barbara Wilson, which company attendance office, please?